طيب بسم الله الرحمن الرحيم. So today inshallah we are going to start chapter 3 talking about public key cryptography and message authentication. طبعا the book takes a slightly different angle from any other book where we discuss the concepts individually, but here it actually the author here tries to group multiple concepts that have some relationship with each other, and as we will see in a minute that actually these are two different concepts. يعني public cryptography and message authentication, these are two separate concepts, but the way that they are grouped together is because of the fact that public cryptography is mainly used for message authentication. So they group based on the functionality, based on the use, and we'll see that in a minute. So first we'll discuss the message authentication, and then we'll jump into public cryptography. So message authentication, as we have discussed before, for authentication we have two types of authentication. We have peer entity authentication, and we have the message level authentication. So here we'll focus on message level authentication. For peer entity authentication, this is done once per connection. So as before we start the connection, for example, if we start مثلا connecting with Amazon website, we do the authentication once at the beginning through user credentials, through certificates, through whatever method, and then this is done once and for all for the entire connection. However, there is another type which is message authentication. Message authentication here focuses on every single message has to be authenticated, and by authentication here we mean that we need to do two things for every single message. We need to make sure that this message has integrity, which means that the message is not altered on the way, and the message should embed into it the signature of the origin. We should always be able to identify that this message is coming from a particular origin, and this origin cannot deny that he or she did not send this message, because his or her signature is actually embedded into this message. So those are the two main objectives. So as we said before, encryption, yes, protects against passive attack, but for active attacks like altering a message or something, we need another technique. So for protection against active attacks, we need to have, as I said, like some signature which is integrated into the message that protects the message from being altered, and at the same time embeds in it the origin's signature. ماشي? So the two important aspects are to verify that the content of the message have not been altered and that the source is authentic. Okay, so those are the two main objectives. Okay, so these are the objectives now. How do we do that? We have two ways. Okay, so first, we know how to do cryptography. We know how to do encryption, and we have studied symmetric encryption. Can we leverage that? Can we use that somehow to provide also message integrity and try to recognize the origin? And the answer is yes. We could use actually encryption, okay, to achieve this purpose. However, in many ways, we see that, well, encryption actually adds more things that we don't need, like, for example, reversibility. Okay, so encryption comes with decryption, right? So the encryption algorithm has to have the ability to be reversible. Okay, so message authentication does not require that. So this added cost comes with also added overhead. And in many ways, we see that to use encryption, and we will see that later, to use encryption for message authentication adds a lot more overhead, because encryption algorithms are by default, by design, they are complex. Okay, complexity is high. So if we use encryption for message authentication, we'll have to pay the cost of complexity. Okay. And the other way is that let's design new algorithms which are optimized for message authentication, such that they achieve these two objectives, okay? And at the same time, we don't need better reversibility, we don't need any other extra overhead to try to make it as simple and less complex as possible, okay? This category of methods, they focus on creating what we call authentication tag. So later on, we'll give another name to the tag, message authentication code. And what this, or how this works is simply that, you know, while we have Alice generates some messages. So unlike encryption, we don't care whether this message is encrypted or not, okay? So we can do the following to the encrypted message or to the original message, it doesn't matter, okay? So what Alice has to do before she sends a message to Bob is that she should append this tag to the message, okay? So this tag should embed into it the two objectives that we talked about. First, if there is any alteration to the message, this tag will become invalid or will highlight the fact that this message has been altered, okay? And at the same time, this tag embeds into it the source, okay? The source can be embedded like in the case of encryption, a form of embedding the signature of the source is the key. And that's why the encryption can be used, because encryption actually implicitly uses the key, and the key kind of identifies the origin, because only the Alice and Bob, they know the key, right? So if I know that this message embeds, or this tag embeds into it the key, then I know that this is coming from Alice and not from anyone else, okay? So that's the idea. So the message itself is not encrypted, or we don't care whether it's encrypted or not. This tag can be generated from an encrypted message or from an unencrypted message. We don't really care. And as we will discuss later on for the protocols, you will see in some security services, this tag is generated after encryption. And in some cases, it's generated before encryption. It doesn't really matter. Both of them have to be done. The order is not really significant. Okay? So these are the two types, whether to use encryption as the main technique to do these two objectives, or to design a special algorithm for that. So we'll talk about some examples of both categories. So this is the model. This is the system model for how we generate these tags. We call them message authentication codes. So the way this is done is that, again, from the message, we have an algorithm, okay? So this algorithm could be encryption algorithm, or it could be a specially designed algorithm to generate this MAC. And the MAC gets appended to the message before transmission. So this is the channel, right? So this channel could be anything. That could be wireless, could be wired, could be even from one application to another on the same machine. We don't care. But if there is any alteration here, okay, this message will be altered, okay? In which case, at the receiver side, what Bob will do, Bob will not try to take the tag and then reverse, because no, that's what's not supposed. This is not what's supposed to happen. What happens here is that now when Bob receives the message with the tag, Bob will take the message and then use the same algorithm, because the algorithm itself, as we will see later, the algorithm for generating this tag is also public, is also well known, right? And then Bob will generate the tag as if he doesn't see the original tag that comes with the message. And then a comparison has to happen. If they are identical, then this message is coming from a valid origin, and this message has not been altered. Okay? But we don't need to take the tag and reverse engineer it and get the message or something. There's no reversibility here whatsoever. That's how how this process works. That's why one of the existing and well-established techniques for producing this tag is what we call one-way, and one-way. It's not two-way, there's no reversibility aslan. It's one-way hash functions. And we are, at least some of us, or most of us, are aware of hashing or aware of hash functions. We'll study this hash function. So the idea here is that hash functions, unlike the encryption, because in encryption, especially block ciphers, they work on fixed size blocks, right? And then produce the same size of the block, but it's encrypted. Here, as we said, we don't actually encrypt the block. We append something to it, right? So what we need to do here is that we have a variable size message. So the message size is not significant here. It could be anything. And then from that, we produce what we call a message digest. This message digest is actually a combination of the message content, such that this combination becomes invalid if the original message happens to have any manipulation or any alteration. That's the idea, يعني, in a nutshell. ماشي? Hash functions themselves, they do not take any secret key. They do not take any secret key. So that's an indication that hash functions on their own are good but not sufficient, right? Because they do not actually embed the identity of the origin in the hash. صح? So they achieve one objective but not the other, okay? So encryption somehow embeds the identity of the sender because it uses the key, okay? But hash functions, they actually produce a signature about the message, but not about the origin. So a natural thing that we can think of is what? Is to combine the two, right? Is to combine the two. So if we combine the two, we can achieve both objectives. And that's one of the common techniques that we can use. We'll talk about it. So to authenticate a message, the message digest is sent with the message, okay? And then, as we said, on the other side, Bob will try to generate the same tag, and if it happens to have identical content with the tag that comes with the message, then it's valid. Type. So these are the three high-level methods of how to do this message authentication code. As we said, naturally, if we take the message and then generate the hash, okay, then we've done half the job. So now this hash supposedly will protect this message from being altered, but it does not embed the origin's identity, right? So what we could do is that after doing the hash, we do the encryption to the hash, okay? So the encryption embeds the identity of the sender, okay? So now we have a message digest that's encrypted, and it achieves both objectives. We append that with the message, okay? And then we send it. And on the other side, we do the operation as we said. We take the original message, we hash it, okay? And then we take this tag, we decrypt it, and then we compare. So that's natural, it's straightforward, right? Type. So is there another way? Here, we use symmetric cryptography, okay? In a minute, we'll start to talk about public cryptography. And as we said before, public cryptography uses two keys instead of one, okay? So for public cryptography, we use private key and public key, okay? Type. For general purpose public cryptography, which is used for encryption, so if we have Bob here, okay, and Alice wants to send a message to Bob. Now we have private key and public key, okay? So if Alice wants to send a message to Bob, what do we use to encrypt the message? We use the public key or we use the private key? Private key is known only to Bob. Okay? So if Alice wants to encrypt a message and send it to Bob, so Alice needs to use the public key of Bob. The public key is well known to everyone. Okay? So Alice has like a chain of keys. Okay? So if Alice wants to send a message to Bob, it grabs the public key of Bob and then it uses that for encryption to send it to Bob. Bob then will use his private key, which is only known to Bob, right? So the question now, does the public key embed in it the identity of the origin? In this case, no. Why? Because the public key is, yeah, everyone knows it. Everyone knows it. Okay? So if Alice now wants to achieve, okay, the integrity and embed its signature so that Bob can authenticate that the message is coming from Alice. Okay? That's what we're trying to do now. So Alice will send the message, which is encrypted using the public key of Bob, but it appends to it the MAC, right? Which has what بقى? The private key of Alice. Okay? Because now Bob wants to authenticate this message that are coming from Alice and not from anyone else. واضحة دي? Okay? So that's why here, as you can see here, so going back, so now going back, you will see that here we use the private key of the sender for doing the message authentication, not the public key. Okay? So this is something specific to the public key cryptography being used as part of the message authentication. طيب. What is the problem here? The problem here is that using encryption is complex by definition. And as we said before, the original objective that we're trying to achieve does not include reversibility or anything like that, right? So the question now, can we try to achieve both objectives without having to do encryption? Because if we can avoid encryption altogether, it would be nice. Because they are complex. They are very, very complicated. So luckily the answer is yes. So the third category here focuses on using neither the symmetric key encryption nor the public key encryption. Okay, so it uses hash, but how can we embed the identity of the origin into the message? We just append it. So append the identity of the source. This secret, okay, that's why it's called a secret value. This secret could be, in fact, the key. It could, in fact, be the key, right? And then we append it to the message first, and then we do the hashing for both. Okay, so this way, we avoid using encryption altogether. And that's the more common method, as we will see later, being used in many of the security protocols that we will talk about. Okay? طيب, what are the properties of these hash functions? Because now we can use hash functions without having to do encryption, right? So what is the properties of this hash function? As we said before, it's one way, so there's no reversibility. In fact, as we will see here, إن هو أصلا reversibility by design should be difficult. So hash can be applied to a block of size of any size, right? Although there is a limit. Just the fact that the size is variable doesn't mean that we have extremely large message and we generate a tag of fixed size. So we'll see there is some correlation, and we'll see why we need to have يعني some correlation. ماشي. But the limit is actually a little bit fuzzy يعني. It's not like very rigid. We'll talk about that. So the hash function produces fixed length output, which is what we call the message digest. Okay. One requirement of this hash functions is that it should be relatively easy to compute, because otherwise we can use encryption. We can go back to using encryption يعني. ماشي. But this should be a lot less complex compared to a encryption technique. So these three are very important. Okay, so for any given code H, it is computationally infeasible to find X such that HX equal to H. Okay, so if I give you كده مثلا, I give you a hash. This is hash, right? Here is the hash. Can you, in fact, find the original message X such that H of X equals to this H? So that's essentially what? لا يعني what is this? This is reversibility يعني. Okay? تبقى مصيبة if I can reverse engineer the message from the hash يعني. It's so bad. That's not what's supposed to happen. Okay? In fact, this should be computationally infeasible. And the here computationally infeasible is an accurate term, because as you said, brute force, we can do everything. ماشي? يعني if I have just one piece of information, the length of the message, I can do brute force, regardless of how many trials I have to go through, but I can do brute force. So that's this property indicates that reversibility should be computationally infeasible. Another thing here is that for any given block X, if I give you not H if I give you the block X itself, okay? So it is computationally infeasible to find Y. And what that means is, can you in fact try to find Y such that in both of them they will have the same hash? Okay. Is this always true? يعني, is it? This is a tricky question شوية. This is called the weak collision condition. بمعنى إن هو the hash algorithm should in fact try to make it computationally infeasible to find Y from X such that Y is actually a function of X, because I give you X, right? Okay. لا, Y is not equal to X. ما هو this is the alteration بقى يعني. ما هو the idea here is that if I give you X, you can manipulate X, okay? And if Bob tries to calculate the hash, he will find that the hash is the same, so the message is valid.
Depends on the message digest size.
Yeah, it depends طبعا on so many factors, but this is computationally feasible. But what I'm trying to say is that computationally infeasible here is an accurate term, and in fact, I can always find two messages such that the hash is the same. Why?
Because the size of the hash is limited.
The size of the hash is limited, بالظبط. Because if the message has a size of m, okay, and the hash has a size of n, clearly m is much bigger than n, right? Okay, so the different combinations on the message is 2 to the power m, which is يعني very large compared to the different combinations of the h. صح كده? So I can never have one-to-one relationship. I can never have a hash which is unique for all values of m. So I will always have collision, theoretically. But the idea here is to make it hard. So the hashing algorithm should in fact be strong enough that makes this collision as hard as possible. Okay? So here, this property talks about the fact that I give you X, which is the natural scenario, okay, that happens in network security or network communication in general, is that Bob indeed has X. And in fact, we should have the assumption that the attacker has X. Okay? So if the attacker has X, ماشي, he can manipulate it to reach Y. Okay? Remember, the hash algorithm itself is public. So if I understand the hash algorithm, ماشي, I can definitely manipulate Y, manipulate X and come up with Y such that the hash for Y is the same. Okay? Is that impossible? No, it's not impossible. In fact, there is a theory. There is a theory called the فاكرة اللي اسمها اللي هي birthday paradox. Okay? So if I give you H, if I give you H in any way, if I give you H, you can in fact find a message that has this H with a complexity of 2 to the power n divided by 2, such that n is the size of the message. Remember, we said that in brute force, for encryption, we can search for the key if we know the length of the key, but there the complexity was a 2 to the power n minus 1. Okay? Here it's even less. Okay? So on average, this is the number of trials before you can guess at the message. But luckily here is the size of the original message, so it's still larger. You see? So this actually identifies, or this signifies the integrity side of the story. In general, but this is called the strong collision resistance. The strong collision resistance here talks about the fact that even if I don't give you X, you cannot find X and Y messages, okay, without any relationship between them, such that X and Y can lead to H. So the only difference between here and here is that in property 5, I gave you X, and you can just manipulate it a little bit, and we'll see an example of this. But 6 talks about all degrees of freedom, so I cannot have any X and Y. I cannot generate 2 different messages with any combination, okay, such that the hash will be the same. At least it's computationally infeasible. Again, it's not impossible, but it's computationally infeasible. ماشي؟ واضح كده؟ Any question?
Why would you decide to make hash functions produce fixed length sizes? Like, wouldn't it be better to make it dynamic sizes to avoid some of the problems with the collision?
To make it, يعني, why do we make it fixed and not variable size? That's a very good question. I think this is because of the fact that Bob has to generate the same hash without looking at the message or at the tag. So the assumption here is that I should actually produce the tag with the same properties. Okay? So we have to agree on a specific fixed size so that I have to generate it. It's unlike, مثلا, if I want to reverse engineer or if I want to reverse the process, then I have something and then I have to reverse engineer it to come up with something else. Here, I don't reverse anything. So Bob has to generate the hash without looking at the message, or at least the message digest itself. So we should agree on the properties.
Sorry to interrupt again. I left my things here and I'd like to take them. I'm so sorry again.
Okay, I think that's the reason, yeah. طيب. So there are, of course, two security properties for the hash, or two approaches to attack the hash. And as we said, we can do crypto analysis. Again, crypto analysis is based on analyzing the traffic or the message or something like this and trying to come up with some collision in an intelligent way, or brute force. And as we said, brute force, if we use brute force, on average, we will reach to a collision with this complexity on average. So a very good example طبعا of a very bad hashing function is what we call the bitwise XOR, or the parity bits. Okay, so an example of how we can produce the hash is actually parity bits, because parity bits, if you know or if you remember from network 1, we can generate the parity bits from the original message by just stacking the message into blocks like this. So whatever the size of the message, we stack it into blocks, let's say like 16 bytes, whatever, 32 bytes, whatever. And then we stack it like this. And then for each column we XOR. So let's say that these are bits. We XOR like this. That's an example of a hash. Why is this bad?
Or you can retrieve the data or go back to the original.
لا بالعكس, you cannot. لا, this achieves the reversibility, ما في مشكلة. يعني انت if you have this, it's hard to reverse and come up with the message. That's not, يعني it's not feasible because you have many combinations. But in fact, you can produce collision very, very easily. If I give you X, ماشي, you have tons of combinations by just يعني switching any bits. So the XOR will be the same. ماشي? So can you imagine how many combinations you can manipulate the message, and the message digest is the same. You can have tons of combinations. يعني. So this is not يعني collision resistance, neither weak nor strong. خالص. ماشي? But this has no strength whatsoever to protect against collision. Anyone not following this? Clear? Okay. That's an example of a bad يعني hash algorithm. طيب, talking about the standard بقى. So one of the very famous hashing standard algorithms is what we call the SHA. SHA, or the secure hash algorithm, has been developed by NEST in FIBS whatever 180. We don't have to really memorize these numbers. So first, it's like similar to موضوع الفيزا structure. They came up with the basic algorithm, and then they come up with a standard called SHA-1, which is again based on SHA. And SHA, in fact, is based on an existing algorithm called MD4, okay, which is the oldest hash algorithm. ماشي? This was like sort of a de facto standard. It's not like standardized, but they have developed SHA based on MD4, and they made it standard. Okay. So SHA-1, okay, was developed in 1995, and it's based on 160 hash size. Okay, 160 hash size. Okay, so of course the message itself could have any variable size. However, as we will see in a minute, if you have a message which is much larger compared to this hash size, after some time the collision becomes more evident, right? صح? Because when M starts to be much larger than N, right, the collision becomes more possible, صح? So we need to maintain certain correlation between the message size and the hash size. So we cannot just increase the length of the message very large. ماشي? So that's why they, in 2005, they came up with SHA-2. SHA-2 proposes multiple sizes for the hash, as we'll see. So these are the standards. So the message, so as we said, that the message digest size, or the hash size, is actually 164 SHA-1. All of these are part of SHA-2. So SHA-2 comes with different hash sizes, like 4 different hash sizes, okay? So here, we don't have like a clear boundary for the message, but it should be less than 2 to the power 64. This is the boundary for the message. Other than this, we have a block size. We didn't talk about blocks when it comes to hash, but as we have seen from the parity bits, is that naturally the message itself gets divided into blocks, right? And then we do like some operations on these blocks in a recursive way, as we will see, okay, to come up with the hash. So the block size naturally for SHA-1 is 512. And there's also the concept of word size. And there's the number of steps. Number of steps is like rounds. So clean rounds for encryption. This is also similar. So we have like 80 rounds or so. So if we look at the message size, it starts to be different here. So when the hash size grows large, we can now increase the size of the message. Okay. So again, the correlation is not 1-to-1. It's like fuzzy relationship, but we should have some correlation. It's not like 1-to-1 yet. All right, so this is SHA-2, which uses 512 for the hash. So the way that this algorithm works is that it's actually similar. What is this similar to? Any similarity like visually كده؟ اللي هو ايه؟ It's somewhat similar بس مش block ciphers بالتحديد. It's similar to one of the أيوة, one of the modes of cipher blockchain. برافو عليك. Yes. It's similar to cipher blockchaining. Cipher blockchaining is like every block is actually based on all the previous blocks. But one fundamental difference here, remember, one fundamental difference is that all of these are not to be used in any way. This is the only one that I use. ماشي? So for cipher blockchaining, for every block, we actually use it as a cipher block. Here, we don't do this because we're supposed to generate one hash from all the blocks. Okay? So we take a message block, and then we use, again, a function, a round function, which is, it's in the standard, they don't even define this function. So this function can, but it does not have to have like transposition and bit manipulation and all of, no. This is like very, very simple function. And that's why here the complexity is very low. So of course, since we are doing like block chaining or block level manipulation, we have initial vector. And here the initial vector is even pre-coded, by the way. It's fixed. It's not like automatically generated or generated based on a pseudo-random function or something. This is actually, in the standard, it's fixed. And then we apply the function, and then we do a modulo arithmetic operation with h, and that's it. So let's try to do the same. So in fact, like h I equals to IBA, equals to the function of mi. So we apply the function to mi, right? And then we XOR that with hi minus 1. And of course here, of course, we have برضو h of I minus 1. Right. So this function is actually an operation on a block with the h I minus 1, and then the result is added to h I minus 1. So again, describing that using a simple mathematical equation like this makes it efficient in terms of hardware, software, anything, and in fact makes it also easy for analysis, right? One thing to notice here is that what if the message is not divisible by the block size? We do a padding. So that's why here we have 1 and any zeros, any number of zeros you want. You have 1 and then any number of zeros you want. And that's why we have L. What is L? L here is the size of the unpadded message. Because if we have padding, again at the receiver side, we need to separate the padding from the original message. So this L stores the size of the unpadded message. And we always have to do that. We always have to store the size of the, even if we don't do padding. ماشي؟ واضح كده؟ Any question؟ واضح؟ اتفضل. طب استنى بس يعني one more. Okay. طيب this is the algorithm, and this is the algorithm for hashing, but what this algorithm doesn't have is again embedding the identity of the origin. Okay, so it does part of the message authentication objectives, but we need the full picture. So HMAC here, or hash-based message authentication codes, tries to put the hashing algorithm into generating the MAC. So the cryptographic hash functions generally execute faster in software than conventional encryption algorithms such as this and so on. So this is the idea of using hash instead of using very complex encryption techniques like this or triple this or something like this. ماشي? So there have been a number of proposals for incorporation of this secret key inside the hash function. And this is the third method that we talked about. So luckily here we can embed the secret key to the message and then do the hash. Okay, this is very straightforward. So HMAC tries to achieve this. It has been issued by HMAC, has been standardized here by RFC, which means that it's standardized by IETF, not NEST. ماشي؟ يعني not that it makes a significant difference for us but this is just for completeness. And has been chosen as the mandatory to implement MAC for IP security. So IETF, because they have to standardize IP security, which we'll study later on. So as part of this, they had to standardize the MAC, and they have developed HMAC for that particular purpose. Okay. So HMAC design objectives is to use without modifications available hash functions. So the idea is that you use a well-established method and just leverage that for the standard. And they decided to use the hash, the SHA-1, to allow for easy replaceability of embedded hash functions in case faster or more secure hash functions are found or required. So they have made that structured in a way that you can actually replace, for example, the round function, you can replace this function easily. Okay. So to preserve the original performance of the hash function without incurring a significant degradation, so all of these are requirements for the HMAC that they have put ahead, and then based on that, they selected the HMAC standard that it achieves all these requirements. Because it's less complex compared to encryption techniques, and it's optimized in terms of software or hardware. It's analyzable easily because we can represent it using some well-defined mathematical equations and so on and so forth. ماشي? So خلينا نبريك هنا. This is simply how to embed the secret value. So we'll talk about this. It's very easy. You would think that you append the secret value and you do it all at once, but they selected to do it on 2 steps, which is it's different from the intuition, but this is what they did. So we'll talk about it. Okay, so what HMAC does is that, as we said, it applies existing hash function, but on two steps. It adds the secret. The secret here is added, which identifies the origin of the message, is added actually in two steps. Okay, and what happens here is that we have what we call iPad and OPAD. So what this tries to achieve is that it takes the secret value or the key, and then it masks it to have the left half or the right half. Okay, so from the key we have SI and S0. Okay, so by doing the masking. Okay, and then we put the first secret value together with the original message. We divide them into blocks, and then we apply the hash. The same hash function that we have discussed before. And this is the initial value, and then we apply the hash. We produce an initial hash, okay? So this hash will add the other secret value or the other half of the key, yani, okay? And then we apply hash again. But this hash is actually very low complexity because it's done on a small part of the or small size message, right? So the complexity here is low, okay? So why do we do it on two stages? I don't know, really. Yani it must have something to do with again the strength or the resistance to the collision in particular. So when it's done in two stages like this, it makes the resistance to collision stronger. Okay. هو secret key يعني is actually قصدك عشان two stages يعني to make it no, I think dividing the key has to do with the block size. So the key is actually like double the block size or something. So the standard actually talks about the key is divided into two parts, and each part is equal to the block size. Okay. Whether this is used for to hide the secret key or not, I don't think so. Maybe, I don't know. But HMAC really يعني uses the approach of two-stage, and again it's recursive like this. Okay. There is the CMAC. The CMAC is kind of strange. The CMAC is based on the assumption that encryption can be used as a kind of hash. Okay. So hopefully, when we use a specific encryption technique, it actually fulfills the property. Of course, we don't need reversibility, but it fulfills the properties of collision, especially the weak and strong collision. Okay, which it should, because again, I mean, the cipher text is supposed to have no correlation with the original text, but it has like some information about the plain text into it. So it should achieve like these properties, and in addition to that, it achieves some other things that we don't need. That's why the CMAC is highly complex compared to HMAC. The complexity of CMAC is like 3-4 times compared to HMAC. So, but the same block chaining is done, but remember here, we don't actually use any of these encryption blocks in any way. We actually use the very last one. That's it. Okay? We use the last block only. So the block chaining is done in this way, but we use the large block only as the hash.
My question is, I think last semester on one course we touched on one of the modes of operations for block ciphers called Galois countable, GCM.
Okay.
Where they do something called AEAD, authenticated encryption with additional layer, which kind of provides you with almost similar objectives as to HMAC. So my question would be, why would you want to kind of embed authentication within encryption, and what difference does it make from HMAC?
What difference does it make?
Yeah, like why would you use HMAC and not maybe Galois countable? Maybe it's more complex in a sense.
Any kind of modes of operation which is used for encryption, the complexity would be more. So encryption in nature and by design, okay, is based on transposition and manipulation. For example, we talked about AES, which is based on matrix multiplication, things like that. So that's by default more complex, of course. So complexity is high, okay? So it remains a question of which of them is more resistant when it comes to collision. And that's why if you can mathematically analyze encryption techniques, which is, in some cases you can, but it's based on information theoretic aspects. So if you find based on this analysis that the collision resistance is more, then you can use that, for example, for devices with resource abundance, where the resource limitation is not there, right? HMAC definitely will be much less complex, and in that case, it can be used, or it's more efficient to be used in resource-limited devices. And that's why CMAC and HMAC, they are there, and they are being used. So CMAC, despite the complexity that it has, it's being used, actually, okay? But in a limited fashion compared to HMAC, as far as I know, okay? So for public key encryption, so this is like a historical idea about public key encryption. It started with Diffie-Hellman. And Diffie-Hellman, as we will study, it's not used for general purpose encryption. It's used for a key distribution only. It's used only for key distribution. And we'll talk about why it's not used for general purpose encryption. So there is, this was the first public key, the first technique that actually used two keys, okay? Now, the best well-known public key encryption, which is used for general purpose, is RSA. And RSA stands for the names of the scientists. And proudly so, we have another one, which is actually done by Gamal. Gamal is an Egyptian scientist who actually did a public key cryptography, which is very, very well known and very, is common, برضو. But of course, when it comes to the standard, some techniques, they dominate. Okay. So this is based on some mathematical functions rather than simple operations of transposition, manipulation, كده يعني. This is based on mathematical.
Sorry to interrupt you, but just before we dive into public key encryption, I just have a question about the last slide.
Okay. All right. So there are some misconceptions when it comes to public cryptography. Many people, they have these misconceptions. So we need to highlight them. So the first one is that public key cryptography is more secure compared to symmetric key, and that's not true. In fact, if you have the same size of the key, symmetric key is stronger. Okay. So public key is not by any means more secure compared to the symmetric key. And in fact, in many cases, public key, because of the high complexity, it's being used more on message authentication rather than as a general purpose encryption algorithm. Okay? So we'll see that. Another thing is that public key encryption is a general purpose technique that has made conventional encryption obsolete. And that's also not true. Because some actually public key cryptography, public key techniques, they cannot be used for general purpose. Aslan, they cannot, such as Diffie-Hellman. Diffie-Hellmans cannot be used for general purpose. Okay? There's a feeling that the key distribution is trivial, because we said that for symmetric key, the assumption is that Alice and Bob, somehow they have the key, and they agree on the key. Okay? And we said that in order for them to have the same key, there is a process that runs in the background, which is a key distribution. Okay? But for public key cryptography, we don't need to have a complicated key distribution process. Why? Because we can simply give the public key to anyone, right? So we can just send the public key. Here's my public key, okay? So there's no need for key distribution. Is that true? Is it really trivial? No. Why? ليه بقى؟ I can give the public key. That's it. Very easy.
Anyone can use those.
How to
أيوة.
identify this? How to identify that this public key linked to this person?
Exactly. So يعني أي حد كده يديني public key. Anyone? No, of course not. طب ما هو the attacker can give me a public key. I can use the I can use the public key of the attacker to encrypt messages and send it to the attacker. So I'm helping the attacker. So we cannot do that, right? So even key distribution is a big process actually for public key cryptography, and that's why we have certificates. We'll talk about certificates in the next chapter, right? So public keys are being exchanged as part of certificate, and certificates have to be يعني verified and vetted by a certificate authority, and يعني there is a huge process يعني ماشي. So this is also a misconception. It's not a trivial process. So this is the security model for public cryptography. As we said before, if we have Bob here, Bob wants to send message to Alice. So Bob here has a chain of public keys. This is Bob's public key ring or chain. It has the public key for Joy, for Mike, for Alice. So if I want to send a message to Alice, then I grab the public key for Alice, and then I use it as part of the encryption algorithm that we will talk about in a minute. And then I send it. And on the other side, the public key and private key are mirror to each other. So if I use the public key, typically for encryption, I can use the public key for decryption. But I can actually use the private key for encryption, right? That's in the case of message authentication. So in that case, I can decrypt using the public key on the other side to authenticate that this message is indeed coming from Bob. ماشي كده؟ So that's the forward security model. So the applications بقى for public key varies depending on the algorithm. So the public key systems are characterized by the use of the cryptographic type of algorithm with two keys طبعا. One held private and the other one is available publicly. And depending on the application, the sender uses either the sender's public key or its own private key, as we said. So for general purpose encryption, decryption, typically what we use is that the sender encrypts the message with the recipient's public key. For message digest or message authentication codes, we sign the message with our private key before sending it as part of the message authentication code for the receiver to authenticate the origin of the message. And there is a key exchange. There is key exchange. Two sides cooperate to exchange the session key. We'll talk about this. So we can, in fact, use the key distribution or the key exchange as part of the symmetric key to have Alice and Bob agree on the symmetric key. Okay, we'll talk about it. So we can now, based on these three functionalities, we can categorize all public cryptography techniques. The RSA is general purpose, as you can see. It can be used for anything. It can be used for encryption and decryption. We use the public key of Bob. For message digest or digital signature, we use Alice's private key. And for key exchange as well, we can use it to, for example, take the symmetric key, encrypt it using the public key, and send it as a message. We can do that, right? And then both Alice and Bob will have the same key. From now on, they can use the key for encryption and decryption. So why don't we just use the public key directly? In some cases, actually, the public key cryptography is even more complex. Okay? Before we delve into some cryptographic algorithm or public cryptographic algorithm, we need to have like a short crash review on modular arithmetic, because this is the mathematical foundation of this. Anyone aware or took a course before in modular arithmetic? You know, like, for example, factorization, you know, the totient, you know, these things?
Yes.
At least some of you, you're not really familiar with that. So of course, this is not in the book, by the way. That part is not in the book at all. But if we need to analyze the public cryptographic algorithm, we need to have like this background. So this is like a very, very short review of this. So first, what does it mean to have a mod? So if I give you like an example, if I give you like 8 mod 7, for example, what is this? 1. This comes from the fact that this is the remainder of the division. So 8 is in fact, 8 is, so if I give you any like y mod x, okay, so you try to get y as multiple division of x plus something, and this something is in fact the answer of the mod. So you're trying to get the remainder of the division. Okay? Type. So is this, what is the properties of this mod function? In other words, if I give you like x plus y mod n, okay, is it actually summative in the sense that this is equal to x mod n plus y mod n all mod n? And the answer is yes, which means that the modular arithmetic is actually summative. Okay? So the summative property is actually preserved as part of this. Okay? Why do we have mod n at the end? Because if you actually take the mod and apply it on each number individually, the summation might be more than n. So we have to take another mod outside. Okay? So if I change this to multiplication, okay, that's in fact applies. So it's actually summative and multiplicative. So the mod has the summative and multiplicative properties. Okay? Type. What is factorizing a number? If I give you a number, let's say 80, for example, and I ask you to factorize this number, what does that mean? This means that we are trying to represent this number using all its divisors. Okay? All its divisors. Okay? So what are the divisors of 80? So naturally you would start from very low numbers. Of course everything is divisible by 1. Okay? So we have to start with 2 مثلا. Is it divisible by 2? Yes. So 2 becomes 40, 2 becomes 20, 2 becomes 10, 2 becomes 5, and then 5. Okay? So that's how you factorize a number like this. So in fact, this is 2 to the power 4 times 5. So that's how we factorize a number, to represent the number using all its divisors. So the theorem is that any number, x, can be in fact represented using the sum numbers of to the power any exponent. Okay? ماشي? So there is a property of this number. This number is actually a prime number. What is a prime number? A prime number is a number which has no divisors but itself, and the 1, of course. Okay? Is 2 a prime number? Yes. That's why we in fact use Zena. If you look at this number, these are all prime numbers. Okay? So any number can be represented using multiplication of prime numbers to any exponent. And that's what we did here. This is in fact what we did here. We factorized 80 into the multiplication of 2 to the power 4 and 5. And all of these are prime numbers. So far so good? Okay. So that's the theorem. So now we're getting يعني a little bit بقى deeper. So what is the greatest common divisor of two numbers? A greatest common divisor of two numbers is to try to find, again, the highest number that divides both these numbers. Okay? So if I give you مثلا greatest common divisor between this 80 and 10, what is that? 10. Why? Because in fact 10 is 2 times 5, and this is actually 2 to the power 4 times 5. So the overlap here is 2 and 5. So multiply the 2, it becomes 10. Okay? So that's easy. So the greatest common divisor is try to find the largest number, okay, that divides both numbers. So if the greatest common divisor between two numbers is 1, what does that mean? This means that we say that these two numbers are co-prime or relatively prime. Okay? So if I give you like, what is the greatest common divisor between 80 and let's say مثلا 21? What is this? 1 actually divides anything, of course. But 21 is in fact 3 times 7. There is no overlap between this and this in any way, right? So it's 1. This means that these two numbers are relatively prime. Relatively prime. That doesn't mean that each of them is prime, because clearly 80 is not prime and 21 is not prime, right? But both of them are relatively prime. Okay? So we're getting there. ماشي? So what is bad totient? The totient of n, which is usually referred to as 5n, is the number of non-divisors from 1 to n. Okay? Is the number of the numbers that do not divide n, okay, from 1 all the way to n. Okay? So if I give you, like, for example, 80, what is the totient of 80? We know that 2 divides 80. We know that 5 divides 80. Okay? Other than this, all the other numbers, it's not divisible. So the totient of 80 is, like, for example, 78. Okay? Which is the number of all the non-divising numbers from 1 to 80. ماشي كده؟ طيب. The good news is also is that this totient preserves the summative and multiplicative properties, which means that totient of x times y equals to the totient of x times the totient of y. Okay? Type, where are we getting with all of this? The main assumption, مثلا, that we need to really keep in mind of all the public cryptography techniques, or at least يعني, the RSA techniques, is based on very important assumption. If I give you a number and say factorize it, okay, a small number like this, we were able to factorize, right? If a number can be factorized by very small prime numbers, okay, and you don't know these prime numbers يعني, in advance, okay, the answer is can you in fact guess these prime numbers that devise this number easily? An example we just talked about here, مثلا 21. Okay? 21 is actually divisible by 3 and 7, and these are prime numbers, right? So it's easy, right? Imagine if 21 دي مثلا is a number which has like 300 digits, okay? And these 300 digits is only divisible by two numbers. Can you get these two numbers systematically using any algorithm? The good news is that, or the good news for the security developers, is that you have to resort to brute force. Which means you have to say, okay, so we have to divide first by 2 and see, and then 3, and then 7, and then 11, and so on. Okay? So you'll have to resort to trial and error. There's no systematic way to do the factorization, okay, in a polynomial time algorithm. You always have to do guesses. This is the main assumption. ماشي كده؟ So we can use that fact and build on it to reach to an algorithm which is really powerful from a security perspective. But remember, there are some other requirements, like for example, reversibility. Okay, on the other side, we also have to be able to reverse that. So how can we do this in such a way that we build on factorization, we build on the factorizing as a difficult process, as a process that has to be done in an exhaustive way, but at the same time, let's make it reversible. So this is the RSA algorithm. It's based on 6 different steps. So first, we select P and Q. P and Q are prime numbers, very large. Each one of them is like 300 digits. Okay? Type. This is done, let's say, at Alice's machine. Okay? Do we need to exchange these numbers? No. So these numbers are local. Okay? No one needs to know about them at all. But these are very, very large numbers, 300 digits. Okay? Since these are prime numbers, we cannot factorize prime numbers. Okay? Type. Then we calculate n. N is obviously a very big number, okay? And it's only the multiplication of 2 prime numbers, which are very large. So if I give you n now, will you be able to get P and Q easily? The answer is no. Okay? The answer is no. And that's one of the main assumptions of this. If you get P and Q, everything is done. Alas. You can do everything. You can do this systematic steps and reach to the public key and private key easily. Okay? But luckily, you will not be able to do that. That's the main assumption. So step 3, we calculate the totient of n, which, because of the multiplicative property, the totient of n is actually the totient of p minus 1, p minus 1. Yeah, I forgot to say that. What is the totient of a prime number, Sahih? The totient of any prime number is actually p minus 1. Why? Because all the numbers before it are not divisible by this number, of course, because it's a prime number, right? Except itself, it's divisible by itself, right? So that's why it's p minus 1, okay? So the totient of n is actually p minus 1 times q minus 1. So that's so far easy. So we can calculate that easily. ماشي? And then we select E such that the greatest common divisor between the totient of n and E is 1, which means that we select E such that E is relatively prime with the totient of n. Okay? So here there are many possibilities, right? So we can select E in multiple ways. Okay? E is actually the public key. So we can select the public key with many possibilities. Because we have many numbers which can actually fulfill that particular equation. All we need is just to get E such that amongst the divisors of the totient of n, there is no overlap between the divisors of totient of n and E. And we have plenty of choices in that case. ماشي? But once we get E and E is the public key, so we can يعني communicate it, no problem. We can بقى إيه calculate the private key. The private key can be calculated using this equation, which is what we call D is actually the multiplicative inverse of E. Okay? This by has unique value. Multiplicative inverse is unique. So you have the degrees of freedom to select E, and we'll see some examples of this. But once you select E, there is only one D that can be the multiplicative inverse of E. Okay? So once we evaluate D, is there a systematic way to get the multiplicative inverse of a number? Yes, we'll talk about this. There is a very simple algorithm which allows us to do this. In fact, in some low numbers, we can guess it. We can actually do the calculation in our head. But luckily for these large numbers, there is a systematic way of doing it. Okay, it's very easy. So once we do this, خلاص. Number 6, we have E, we share it. We have D, we keep it. And that's it. Okay. Type. So now we have the private key and the public key. How do we do that? The encryption, the process of encryption and decryption. That's how we do it. So the cipher text is in fact the message to the exponent of the public key, assuming that we do encryption, not message authentication. So the message to the power of the public key equals to the ciphertext. So if you know the ciphertext and you know E, it's very hard to get to the M because you don't know D. And in order to know D, you have to be able to go all the way of knowing P and Q, which is very hard to guess. And then at the other side, at the receiver side, we get the ciphertext to the power D. Okay, we get them. So we need to prove that the reversibility in that case. So how can this achieve the reversibility? So we know that from this process, okay, we have done a lot more than just factorizing. Why do we do this? In order to have this reversibility between these two steps. Okay, the reversibility is coming from the fact that D is the multiplicative inverse of E modulo N, modulo totient of N. Okay. So how do you prove the reversibility? C to the power D here. C is in fact M to the power E mod N. All of this to the power D mod N. So we need to prove that this actually reduces to just N. So from this we can use the multiplicative property of the mod. So we can say that this is in fact M to the power ED mod N. Okay. So what is that ED? ED here, mod the totient of N equals to 1. And what that means is that ED can be represented using multiple totient of N plus 1. So this is the definition, the basic definition of mod. Okay, so ED can in fact be represented using the totient of N using this simple equation. Okay, so we'll substitute that here. So equal to M to the power I totient of N plus 1 mod N. Okay, so This is in fact m mod n multiplied by m to the power mod n. That's it. Okay. So these two terms, we need to say that this term is equal to 1. Okay, in order to end up with the m. And m mod n is in fact m, which means that m and n are relatively prime, which means that there is no divisors between m and n. Can this be, by the way, many of the books actually, they neglect this process. They neglect this idea that m and n, they need to be relatively prime. Can that be achieved in practice easily? Yes. Why? Why? Because n is actually p and q only, and these are very, very big numbers. So m can be selected with very, very high degrees of freedom. Okay? That's easy. That's easy to do. So m mod n is in fact m, right? So this is m. ماشي كده؟ So جه بقى واحد يعني scientist اسمه ايه؟ Euler. So Euler's theorem says that m to the power twoshent of n multiplied by any number, mod n is in fact 1. So this is based on Euler's theorem. Okay? So by doing that, we prove the reversibility based on Euler's theorem. And in fact, Euler's theorem is can simplify many things يعني, for us. We'll do some, in the assignments وكده, we'll do some operations on these things. Like for example, if I give you مثلا 2 mod 7, what is this? It's 2, right? So this is easy. But if I give you something like this, what is this? That's not easy, right? Okay, 2 to the power 90,000, mod 7. How do you calculate this? It's not easy, huh? But we can do a little trick. We can say that, what is the twoshent of 7? 6, صح? So we should try somehow to have 2 to the power 6. Okay? Can we do this here? Yes. صح كده? So we can say 2 to the power 6. Okay? All of this multiplied by ايه؟ multiplied by على 3 على كده كم؟ multiplied by 3 تطلع 3000 multiplied by 2 يعني كم؟ Someone do the math. Multiplied by 30 multiplied by حاجة بتاع 15,000 something like that. ماشي؟ mod 7, right? So 2 to the power 6, if you get the mod inside, it becomes 2 to the power, the twoshent of 7, okay, mod 7. What is this? 1. So this whole thing is actually 1. ماشي? So using this Euler's theorem, we can يعني, use it to simplify things. ماشي? Another way of doing this, by the way, is like if you say 2 to the power 3 mod 7, all of this multiplied by 30,000 or something like this. صح? What is 2 to the power 3? 8. 8 mod 7 is also 1. This whole thing is also 1. Okay? So we can do these tricks to simplify it. Any comment or anything regarding the reversibility issue? Okay? But there is a condition, as I said, there is a condition that many books actually, they ignore it. But as we said, this condition can be easily achievable. And in fact, even if M is divisible by P or Q or anything, we can use encoding to actually get rid of this. So it's easily achievable.
So as we said, doing the steps to to get the public and private keys.
Right.
E was the public, D was the private. What
Right.
if I reverse them, just use this as the private, this is the public? Does it do any harm? Or
لا it does not. لا يعني we can use D for example as the public يعني you could, yes. I don't see anything that would stop you from doing that.
just getting two keys, the concept of getting two keys, one of them would be private for me just to keep it.
Yeah, in all cases, in order for you to break this, again, you have to reach to P and Q. If you reach to P and Q, then everything is done. Because the whole idea is based on the difficulty of the factorization, right? And M is a very, very large number. So that's the main idea. But if you reverse and use D and E in any way, it doesn't matter. ماشي? So that's فضل.
How to find two prime numbers? And it's not easy.
It's lookup. يعني there are lookup tables.
Some people
They are available يعني. They are available. Yes, they are available.
You need to trust that they are prime.
That's a good point. يعني you have to verify that these are prime.
Verification takes time, as you said.
Yes, but it's a one-time process. صح? It's offline. It can be done offline. I do it once, خلاص. And whenever I select any of these prime numbers, I can use them. I don't have to every time verify that these are prime numbers before I use them. Okay? So that's يعني an example with clear numbers. So if we have the N is 187, and we have E as 7, and we have the D as 23. Okay? So that's how we do it. So 88 to the power 7. Of course, we can do that using like a program. يعني. We don't have to calculate it, luckily. ولا حتى sometimes not even using calculator or something. يعني. You can use programs to do that. But N is 187. As we have talked about the example of 80, we were able to factorize it easily because, again, 2 is actually a divisor of 80, and we started to simplify there. But 187, can you guess, مثلا, what is the divisors of 187? Eh? لا هو 187 is not prime, but 187 is divisible to two prime numbers. Can you guess what these prime numbers are? What I'm trying to say is that for a low number like this, visually we cannot even guess the divisors, right? We cannot, صح? I guess this is actually the two prime numbers, طبعا, because I know this from before. I guess it's 11 and 17, something like that. So if you multiply these, you would come up with. But can you really guess these numbers easily? Even the numbers, يعني 187 is not that big. So imagine that if it's like 300 digits. It's not an easy process. Even if you have calculator, even if you have a program. The only way you can do that is to do brute force. So there is no polynomial time algorithm to do that. That's the idea. So this is the plain text. If we use the D and we do this reverse operation, we come up with the same plain text again. So it's reversible based on this Euler's theorem. Okay? طيب. The idea now is that so this is actually the algorithm again. So in order to produce the example that we just talked about, the P and Q are 17 and 11. So if you multiply that, we get the 187. And this is how to systematically perform the 5 steps that we talked about in order to come up with the D and E. One thing to notice here is that in order to get E such that E and 160 is 1, we have here plenty of choices, okay? For example, one of them is 21 that we talked about. Here we use only 7. صح? So we have multiple choices. صح? So 7 is relatively prime with 160. 21 is also, because 21 is actually 3 times 7, which also are not divisors of 160 by any means. So you have plenty of choices in that case. We select 7, but once we select 7, we can have only 1D. It's a unique multiplicative inverse for the mod n, which is in that case 23. So how did you calculate that 23D? That's the question now. How can we? Eh? Okay, so there is a systematic process to do that. Okay, there is a systematic process. And this is what we call a extended Euclidean algorithm. So the Euclidean algorithm is being used, in fact, to calculate the greatest common divisor. Okay, extended Euclidean algorithm is to go in reverse direction. Okay, and to go to the reverse direction, you can calculate the multiplicative inverse. Okay. So the main idea here is that, remember, our objective here is to calculate the multiplicative inverse, is that we know that D times E, okay, mod n is equal to 1. What does that mean? This means the tangent of n, is equal to 1. And what that means is that we have D times E equals to I tangent of n plus 1. صح? Any multiplication of A. So what we will try to do is the reverse operation, which means that we will try to represent 1 in terms of the E and D and the tangent of n, which means that the 1 equals to E times something plus minus I times the tangent of n. Why do we do it this way? هنعرف دلوقتي. ماشي. So the Euclidean algorithm is used, as I said, to calculate the greatest common divisor in a systematic way. Of course, we were able to do it visually in many cases, but in order to do that in a systematic way, okay, there is a straightforward method. And this method, it says that if I want to calculate the greatest common divisor of 7 and 160, I need to represent the higher number as a multiplication of this lower number plus something. I have to convert it to this way. So I have to calculate this number, ماشي, such that the multiplication of 7 and this number plus any number is in fact 160. Why do I do this? Because the good news is that the greatest common divisor of these two relatively big number can be reduced to just this and this. Okay, so the greatest common divisor of 7 and 160 is in fact the greatest common divisor of 7 and 6. That's all. Okay, so this way I was able to reduce to a number. And by the way, what is the answer for this? We know that 7 and 160 from the previous example, we know that these are relatively prime, which means that the answer is well known to be 1. I know that. صح? I know that, but that's not the objective. The objective is to be able to calculate the multiplicative inverse. Okay? Of this 7, the multiplicative inverse of 7. ماشي? So in order to do that, we can reduce the greatest common divisor between 7 and 160 to 7 and 6. So now we have to again take the high number and represent it using the low number times something plus 1. So this in fact reduces to the greatest common divisor of 6 and 1. What is the greatest common divisor between 6 and 1? Once we reach to a low number, a prime number, then we stop. خلاص. Okay? So it's 1. Okay? So why do we do this? The idea is not this. The idea is to go in a reverse direction. is to go and reverse these operations. What we want to achieve, like here, is in fact the fact that 1 can be represented using the 7 multiplied by something plus the quotient of 60 multiplied by something. Once we have this form, صح? We know that this is in fact the multiplicative inverse. صح? So that's what we need to reach. And of course, this will be a negative. There is a negative sign here. So once we reach to that form, we know that this is the multiplicative inverse. So we can go in reverse direction and say, we know from this that the 1 is in fact 7 plus 6 multiplied by minus 1 from this step. Okay? ماشي كده? And in fact, the 6 is in fact 160 and 7 multiplied by minus 22. So we get this form, and then we reduce it to that. So if we do this simplification, we end up with the 160 on one side and the 7 on one side. Once we reach that, then we're done. What is this number? It happens to be 23. So we stop here and say this is the multiplicative inverse of 7. And that's in fact the private key. ماشي? Of course, we can do that for low numbers, but for very, very large number of 300 digits and so on, you have to resort to programs, of course, to do that. But these systematic steps allows you to perform that operation regardless of the large number. We can do that in reverse operation like this recursively using a simple loop, recursive loop in a program, and we can do it. Okay, and this is polynomial time algorithm. ماشي? And the multiplicative inverse here is unique given the public key. ماشي كده? So we'll open the discussion for the Diffie-Hellman. Just give a simple introduction, and then we'll continue next time, inshallah. We have 2 presentations, huh? Okay. Yes, okay, I know. But the SD is motivated by the fact that stop, please. I know.
I have an appointment later, so I can.
Okay. لا احنا we're here until 8. This is the official time, صح؟ أو يعني 10 minutes to 8 يلا مش مشكلة. Okay. All right. So we'll just يعني give 1 or 2 slides and that's it. So Diffie-Hellman بقى. Diffie-Hellman, as I said, Diffie-Hellman is in fact chronologically, Diffie-Hellman was invented or was actually developed before the RSA that we just talked about. This is the older one. And in fact, this is based on a completely different theory. Not بقى factorization خالص. ماشي? So a number of commercial products employ this key exchange technique. As we said, Diffie-Hellman is not used for encryption خالص. Okay, cannot. We'll see. يعني. The purpose of the algorithm is to enable 2 users to exchange a key. That's the only usage for it. The algorithm itself is limited to the exchange of that key. It depends on the effectiveness of on the difficulty of computing the discrete logarithm. And what that means is, if I give you 2 numbers and say a to the power x equals to y, if I give you this equation and I give you a to the power x equals to b مثلا, okay? If I give you this and I tell you, if I give you a and b and tell you what is x, how do you calculate x? Huh? Using the logarithm, right? So x is in fact log b divided by log a. صح? It's very simple. Okay? So I tell you, what is a to the power x mod n equals to b? I give you a and b. Yalla. Give you both, all these numbers. What is x? Can you take logarithm here? You can't. Okay? That's the definition of a discrete logarithm. It's not a normal logarithm. It's actually the discrete logarithm, right? So if I give you a, n, and b, and ask you about x, again, there's no systematic algorithm that allows you to calculate x in a polynomial time. Especially if we have certain property between a and n. Okay? If a and n has certain property, then that makes the estimation or the calculation of x very hard. What is this property? It's called what? لا 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 لا. We call a is a primitive root of n. And what that means is a is a primitive root of n. What this means is that for each value of x, okay, you get a unique number of b, which means that for every value of x, you can never have the same b for two values of x. Of course, when we talk about the modulo arithmetic, as you can imagine, there are multiple numbers, if they are not primitive root of each other, for different exponent, you can get the same answer, صح? Many numbers are like this. But if a is a primitive root of n, then for each value of x, you get different b. Okay? So in that case, if I give you a, n, and b, guessing x becomes very hard. Very hard. ماشي؟ هتقول لي برضه نفس السؤال. طب ازاي انا اعرف ان ده primitive؟ اقول لك نفس الإجابة. The same answer. There are lookup tables for all the primitive root numbers. These are already available. If you search on the internet, you will find tons of these lookup tables with numbers that are primitive root of each other. Okay? So for me, it's not hard at all to search and come up with two numbers and bring it in the exam. Very easy. Okay? ماشي كده؟ This is the main theory based on which the Diffie-Hellman is designed. Not بقى the logarithm, the discrete logarithm. This is the definition of the discrete logarithm. ماشي? So we'll talk detailed algorithm because it's a bit يعني it's a bit engaging. But we'll talk about the detailed algorithm next time عشان بس